Okay, let's dive right into this. Welcome to the Explainer. Today we're going to do something a little different. We're actually turning our time together into an interactive investigative lab. We're getting hands on with the fascinating science of mixtures. We're going to look at exactly how the world around us is put together, and honestly, more importantly, how to pull it apart. And we're going to use the exact same principles that drive life saving medical tests. So zip up those virtual lab coats, because we've got a real mystery to solve together.
To kick things off, I want you to just think about an everyday science mystery for a second. Treat this as your very first assignment as my lab partner. Think about this. If you scoop up a glass of muddy water from a puddle outside and just leave it on a table, eventually all that dirt settles right to the bottom, right? But if you take a glass of milk and leave it out, okay, aside from it eventually smelling terrible and spoiling, those white particles don't just fall to the bottom to leave perfectly clear water sitting on top. Why is that? Like, what invisible forces or structures are actually at play here? It's so natural to just pause and ponder these kinds of fundamental questions about the nature of matter. And honestly, answering this specific question about settling particles, it unlocks a whole world of practical science. It literally helps us understand the fog you drive through on your morning commute, how we make butter, and even how doctors separate your blood components in a medical lab. The whole shebang basically comes down to understanding the hidden architecture of heterogeneous mixtures.
All right, let's move into our first experiment and really focus in on this activity on heterogeneous mixtures. We're going to recreate activity 5.1 from our source material right here in our virtual lab. Okay, imagine we've divided into three groups. Group A takes a beaker with 50 milliliters of water and stirs in a single spatula of common table salt. Group B, they take their 50 milliliters of water and stir in a spatula of chalk powder. And Group C takes their water and adds just a few tiny drops of milk. Now, I want you to mentally predict what happens when we stir these specific ingredients. What's it going to look like immediately, and what happens if we just leave them completely undisturbed for a few minutes? Let's check our lab notebook and see what our visual observations tell us. For beaker A, the salt and water, if we ask are particles visible, the answer is a hard no. It's perfectly uniform. That salt has completely dissolved, creating a homogeneous mixture, which we call a true solution. Now, beaker B with the chalk powder, totally different story. Those chalk particles are super easy to see, the water looks really muddy, and yeah, if we wait a little bit, those chalk particles are absolutely gonna settle right at the bottom. But beaker C, the milk and water, well, that's our wild card. The liquid looks cloudy, sure, but we can't actually see the individual particles with our naked eye, and crucially, they do not settle over time. So we're looking at three wildly different behaviors here. To really wrap our heads around what's happening at a microscopic level, we have to go beyond just looking at these beakers in normal room light. We need to bring a new tool into our virtual lab, the laser pointer. We're going to direct a super thin beam of laser light straight through the side of each of these three glass beakers. But before we do, we need a strict laboratory safety rule straight from our sources. Absolutely do not look directly into the laser beam. It can cause irreversible eye damage. So we'll observe the beam safely from the side, totally perpendicular to the light's actual path. Okay, are you ready for the big aha moment? When we shine that laser, we are hunting for something called the Tyndall effect. By definition, this is the scattering of a beam of light by dispersed particles in a colloid or suspension, which actually makes the physical path of the light visible to our eyes. Have you ever been walking in a really dense forest and seen those bright, distinct rays of sunlight just piercing through the small gaps between the leaves? Well, that is the Tyndall effect happening right there in nature. The sunlight is actually being scattered by tiny dust particles or mist suspended in the air. And this brilliantly illustrates exactly what's happening inside our beakers. In beaker A, our homogeneous salt water, the light path is totally invisible. The dissolved salt particles are simply way too tiny to scatter the light, so it just passes straight through. But looking at our heterogeneous mixtures, both the chalk water and the milk water, the laser beam literally lights up like a glowing line inside the beaker. So even though the milk mixture looked kind of uniform to our naked eye and didn't settle, it absolutely still contains suspended particles that are large enough to scatter that light. So the crucial takeaway here is how we classify these mixtures based on our lab results. The salt water is a true solution. It's homogeneous, has incredibly tiny particles, and zero light scattering. The chalk water is a suspension, a heterogeneous mixture with large particles that settle down over time and definitely scatter light. And our mysterious milk and water, well, it belongs to a very special category called a colloid. Colloids are heterogeneous mixtures too, but their particles are kind of a moderate size. They're uniformly dispersed, which means they don't settle due to gravity, but they are absolutely large enough to trigger the Tyndall effect and scatter light.
Now that we've successfully classified these different types of non-uniform heterogeneous mixtures, it brings us to the second phase of our investigative lab. How in the world do we pull them apart? As our source material points out, separation isn't always a walk in the park. Imagine trying to perfectly separate all the individual ingredients in a glass of lemonade after they've already been mixed. For heterogeneous mixtures, we have to kind of play detective. We have to exploit the physical differences between the components, things like their size, their solubility, or their density. This brings us perfectly to activity 5.6 and a really fantastic piece of laboratory glassware called the separating funnel. Imagine you're washing dishes and some water falls into a container that still has leftover cooking oil in it. What happens? They don't mix uniformly at all. They form entirely separate layers. We actually call liquids that refuse to mix like this immiscible liquids. And the separating funnel is just perfectly designed to take full advantage of this exact behavior.
Let's follow the precise recipe from our text. We're going to pour a mixture of exactly 5 milliliters of mustard oil and 20 milliliters of water straight into our 50 milliliter separating funnel. Once we pour it in, we just step back and let it stand entirely undisturbed. Almost immediately, you're going to see a distinct yellow-colored layer of mustard oil forming right at the very top, with a perfectly clear layer of water sitting just below it. The physical mechanics at play here are beautifully simple, and they rely entirely on density. Because the liquids are immiscible, they're never going to form a solution. The mustard oil is physically lighter, meaning it has a lower density, so it floats and forms the upper layer. The water is denser, so it naturally sinks to become the lower layer. To separate them, we just slowly open the little valve at the bottom, that's called a stopcock, and carefully drain the heavy water into a flask. Right before that yellow oil reaches the bottom, we close the stopcock. We dump out the tiny bit in the middle, and boom, we have our two pure liquids completely separated. Now, you might be wondering, why does this matter outside the chemistry lab? Let's pivot and look at a brilliant real-world application. Sometimes, heterogeneous mixtures, like colloids, won't separate just by letting them sit there, and they certainly won't separate through a simple paper filter either. A perfect example of this is human blood. Blood is basically a mixture of cells suspended in plasma. So to perform medical tests, doctors really need to separate those heavier cells from the lighter liquid. To pull this off, they use a process called centrifugation. Think of being a kid on the playground, playing that game where you cross arms and hold hands with a friend, and you both spin around in a circle as fast as you possibly can. You feel that really strong pull dragging you outwards, right? Well, that's centrifugal force. Centrifugation spins a mixture at incredibly high speeds, physically pushing the heavier particles outward and down to the bottom, leaving all the lighter liquid floating at the top. Our source material highlights this absolutely brilliant, low-cost invention called a paperfuge from Activity 5.8. It's literally made of just a cardboard disc and some string, and it spins rapidly to achieve this exact life-saving separation. It's a total game changer.
Let's look at one more incredible separation technique for our lab session today: coagulation. Let's say you have that muddy water from our very first question. The larger dirt particles might settle over time, sure, but those extremely fine suspended particles, they'll stay cloudy for days on end. So how do we speed this up to actually get pure water? Well, we can add a white crystalline chemical substance called powdered alum, or Fitkari. The alum essentially acts as a coagulant. It literally forces all those tiny, fine, suspended particles to clump together into much larger, heavier masses. And once they're clumped up, gravity simply takes over. They sink rapidly to the bottom in a process called sedimentation, leaving perfectly clear water right on top.
All right, we have covered a ton today. We went through solutions, suspensions, colloids, the Tyndall effect, separating funnels, centrifugation, and finally, coagulation. You are now officially equipped with the knowledge of exactly how matter mixes and, more importantly, how to pull it apart. So I'm going to leave you with a rather provocative challenge straight from our text. If you were camping outdoors, miles from civilization, and ran dangerously short on clean drinking water, how would you use these very techniques, these exact scientific principles of separation to survive? Really think about it. Science isn't just trapped in a lab, it is literally everywhere around you. Thanks for joining me in this explainer, and keep questioning the world around you.